There are 4 1.6 question types you're likely to see on the AP exam. In the next few minutes, I'll show you how to turn these graphs from a mess of squiggly lines into something you can read in under 10 seconds. Then I'll show you exactly the 4 question types you're likely to encounter on the exam. And here's the thing, with PES, you don't need to memorize the shape of every graph. You need to understand how it's put together. Fair warning, if your electron configurations aren't rock solid yet, this topic is going to feel like a foreign language. And that's not on you, that's just how the sequence works. Go lock those down first, then come back. Then this will actually click. A spectroscopy graph is broken down into energy levels, then orbitals, the same as electron configurations. This graph of potassium mirrors its electron configuration. And one trick that will help, picture the nucleus of an atom as being right here at the origin, then build from the core out to the valence. Potassium has one orbital in the first energy level, and that's this single peak on the left, which makes sense since the first energy level will be closest to the nucleus. There are 2 orbitals in the second energy level, represented by this pair of peaks. The 2 third energy level orbitals match up with this grouping, and the single 4th energy level orbital matches this final peak all the way on the right. At a glance, you should be able to break up the groupings into energy levels. Then break up the peaks into orbitals. The order of the peaks matches the organization of the electron configuration. So if you can write an electron configuration, you can easily interpret one of these graphs. Notice that the energy levels for the groupings was still maintained based on the number in front of each orbital. The height of each peak, as labeled on the vertical axis, indicates the number of electrons in each orbital. Each of the s orbitals for potassium contains 2 electrons, and that's why each of those peaks comes up to 2 on the graph. On the exam, this will be referred to as signal intensity and not peak height. The peaks representing the p orbitals come up to the top line, because they both contain 6 electrons. The 4s has a signal intensity of 1 because it contains 1 electron. If you understand electron configuration and the layout for these graphs, you can write the electron configuration directly from the graph, even if you don't know the element. And yes, you'll have the periodic table next to you during the exam for reference. If spectroscopy questions show up in the free response, they'll be relatively simple. It's the multiple choice questions that are going to get you. Let me start with examples of each of the exact questions that have shown up in the free response, and we can build knowledge from there. When writing the electron configuration, I start with the orbitals, because they're always in the same order. Don't waste time memorizing the order, and don't copy from a list when you're doing the practice. Using your periodic table on every practice problem will ensure you understand how to put it together when you get to the exam. I do have some good news. Since d orbitals make things weird, they won't show up on these graphs. That does limit you to only the first 20 elements on the periodic table. After I write the orbitals, I check the peak height so I can put the numbers in for the electrons. Remember, your final answer should be clear and well organized. Don't be lazy. Rewrite it if you need. Now, referencing your periodic table, you should be able to identify this as beryllium. Using the symbol for the element is fine, especially if you're not sure how to spell beryllium. I'm going to follow the same steps for the next one. First, the orbitals. 1s, 2s, 2p, 3s, 3p. Always the same order, just use your periodic table. All 3 s orbitals have a peak intensity of 2, and the 2p has 6, and the 3p comes up to 3. Rewrite it to clean it up, and that's the electron configuration for phosphorus. Did you notice that I'm circling all my answers, running through the same process for solving each question, and creating consistent systems? You don't have to do things my way, but find procedures for solving problems and write them down. Build your own small habits for tracking details and write those down too. Writing it down helps your brain store things better. And these systems will turn you into a problem-solving machine. You'll not only do better on the AP exam, you'll get better at all types of mindful work. I do treat this channel as a test prep, but I love teaching and learning chemistry because of how much it trains students to become more capable thinkers and problem solvers. The work you put in here will stay with you long past the AP exam. Another variation that's appeared in the free response provides you with an incomplete graph and asks you to draw the missing peak. To earn the point, you'll need both the peak height and the relative position. I'll start by writing out the electron configuration to see what's missing. The question does identify the missing orbital, and now I have the peak intensity. To position that peak, just remember that peaks from the same energy level are grouped together. As long as you place the peak close to the 3s, you're good. Since there's 4 electrons in the 3p, the peak height does have to be exactly 4. The actual position of that peak is right here. The true binding energy spaces these two out a little more than you might expect, but as long as your peak is reasonably close to the 3s, you'll pick up the point. Writing the electron configuration, identifying the element, and drawing in the missing peak are the trio of questions that have shown up in the free response in the past. They're also fundamental questions for these graphs, so do some practice and ensure your understanding. Next are the conceptual applications, likely to be in the multiple choice. There's 2 questions from the practice exams that relate to binding energy and peak intensity. They don't release the multiple choice questions from the exam, but everything I've researched over the past few years has told me that the official College Board multiple choice practice exams are the best indicators of what you'll see on exam day. That's why I've analyzed that entire set to make sure I'm covering exactly what you need. Before now, each graph has shown all the peaks for a single element, but these questions are going to be comparing the same orbitals from 2 different elements. Peak X either belongs to sodium or potassium, so go to the periodic table. They're right here, and you need to watch out for the trap. Most of the time our focus is on the valence electrons, and both of these have 1 valence electron. That's why this answer is here. If you go too fast and assume the graph shows you the valence, you'll pick D. But all the comparison graphs show the same orbital. This one's showing you the 3s orbital from both elements. Answer D even reiterates this. Make sure you read carefully. One word or symbol can change the answer to a question, and they will always include the trap in the answer choices. I'm going to write down the electron configurations, then focus in on the 3s orbital. See how the difference jumps out at you? Take the time to write it down. And, like many questions on the AP exam, this one's looking for a specific justification based on peak intensity. Peak intensity is equal to the electrons in that orbital. Since peak X has a height or intensity of 2, that one is potassium. Now that I've identified my answer, let me take a look at the choices. And the only one that matches my opinion is option C. But double check the justification, because sodium has 1 electron in the 3s. Yes. The justification in the multiple choice may not be worded the same as your thought process. That's why I write everything down. It makes it easier for comparison and improves my chance of picking the right option. The multiple choice questions also dive a little deeper into placement on the x-axis. So let's take a minute to talk about binding energy. The binding energy is the force of attraction between the nucleus and the electrons in each orbital. Unlike most graphs, spectroscopy graphs start at a high value, then get lower as you go to the right. Don't worry about the units on binding energy, by the way. You won't be doing any calculations with these. The electrons with the highest binding energy, those closest to the nucleus, will appear on the left. That's why I like to picture the nucleus near the origin. Each subsequent peak decreases in binding energy, so it moves to the right on the graph, almost as if these peaks were arranged based on their distance from the nucleus. Just like Coulomb said, the attraction decreases with distance. This is a simplification that's not completely to scale, but for analyzing these graphs, it is a good mental trick. Whenever you think Coulomb, remember charge and distance. In the case of electrons, the force of attraction comes from the nucleus and is dependent on the number of protons or nuclear charge. The distance from the nucleus is based on the energy level and the orbital occupied by the electron. But these questions always compare the same orbitals, so the only difference you're looking for is the nuclear charge. This is the connection that's going to be tested in the following questions. The main point to remember is that the higher the nuclear charge, the greater the binding energy. In functional terms, the higher the atomic number, the further to the left the peak will be on the graph. Which brings me to question 4. The peak on the graph is the 3s for chlorine. You're asked to draw the 3s for silicon. Where do you look when comparing elements? The periodic table. The elements are here, and what I'm looking for is the atomic numbers, 14 versus 17. So chlorine has the higher nuclear charge. That means the 3s peak for chlorine will have a higher binding energy. The peak for silicon should be further to the right. The exact placement doesn't matter as long as you're to the right of the peak given. These will typically be multiple choice questions, so you'll have to pick the correct justification instead of writing it out. But if you can write it, you can pick it. That might not be the best catchphrase. Since I'm drawing silicon's peak, I'm going to phrase my justification based on silicon. I identified the lower atomic number meant that it was further to the right, but in formal terms, a lower nuclear charge leads to a lower binding energy. To hammer this home, check out a graph of all 1s orbitals. These are the 1s peaks for the first 4 elements on the periodic table, starting with hydrogen, helium, lithium, and beryllium. Notice that as the atomic number increases, these peaks move to the left. providing a clear indication that binding energy is proportional to the nuclear charge when dealing with the same orbital. This one's a bit more complicated, but applies the same principle about binding energy. The question asks you to infer something about the graphs, so I would skim the answer choices to figure out where I need to focus. There's two parts to each. The first part compares the nuclear charge, and the second part identifies the positive ion and neutral species. Quick test-taking tip. When your answer choices look like this, ignore them. Highlight what you're looking for, decide for yourself how the two graphs compare, then go back and match your answer to the options. The major difference between these graphs is that the one on the bottom is shifted way to the left. All the orbitals have a much higher binding energy. That means that species B has a higher nuclear charge. To figure out which one's the ion, I'm going to look at the periodic table. According to both graphs, the neutral atom is neon. This matches the electron configuration if no electrons are gained or lost. That means the ion could be one of these two. Remember, the ion is positive. Since cations formed by losing electron, sodium and magnesium ions have the same electron configuration as neon. Both of these have a higher nuclear charge than neon, so species B must be the cation. Now that I've written down my conclusions, I'll check the answers. The description of the difference in nuclear charge is based on species A, so let me alter my conclusion. I hope you're taking notes on both the chemistry and the amazing test-taking tips that I'm providing. Choices A and B say that species A has a larger nuclear charge. Those are out. What's the difference between C and D? C says that species A is the cation, so that one's wrong too. Don't just assume that D is correct, always double check. Has a small nuclear charge, and B is the ion. That's consistent with what I found. D is the correct answer. Here's what I want you to take away from this video. First of all, I recommend reading the orbital order from the periodic table as you work through the practice problems. This will drill that process into your brain for both electron configuration and spectroscopy questions. The free response question that appeared in years past evaluate the graph of a single element. These haven't shown up in the exam recently, but if they're not there, I bet they just moved them to the multiple choice. Both the multiple choice from the practice exams compared the same orbitals from different elements. The difference was based on either peak intensity or binding energy. For peak intensity, write both electron configurations, circle the orbital in question. For the latter, remember that binding energy is on the horizontal axis and that the nuclear charge is given on the periodic table. This connection can also be applied in various ways, so slow down and write out your thoughts. If you made it this far, thank you. I created this channel because there's nothing better than watching a student go from confused to confident. If you found this video helpful, please hit subscribe. I'm trying to build out the 100+ videos required for covering all of AP Chemistry, and every subscriber tells me it's worth finishing. And remember, don't just memorize it, understand it. See you in the next one.